So recall that when we were talking about limits, the idea came up that when we looked at a function, we wanted function values immediately to the left and function values immediately to the right of a point are equal for the limit to exist. So let's just look at a sketch of a function. And here's our function. And let's say we're interested at some point x is equal to a. So looking at this graph, let's say this is the graph of f of x, we know that the limit as x approaches a of f of x does not exist. And the reason it doesn't exist is because I need all values of x around a, not including a, to be approximately the same thing as x gets really close to a when I look at the function values. And so we see specifically here that if I look to the left, the function values are significantly lower than if I look just to the right. But just because the limit as x approaches a of f of x does not exist, we can actually still talk about what's called one-sided limits. And one-sided limits basically just ask the question, what's happening to the left and what's happening to the right? And I'm okay if those are not equal. In other words, I'm okay if the limit doesn't exist. I can still look at what's called the left and right-handed limits. So the left-handed limit looks something like this. Now, on the graph, the left-handed limit, the word left, really is referring to I'm looking at x values to the left of a. And the notation looks like this. It's the limit as x approaches a, and then I put a little minus sign in the superscript of the a to signify that I'm looking as x approaches a from the left. So you see that the limit of this function as x approaches a from the left of f of x will exist. And similarly, we can define the right-hand limit. And the notation here is going to be similar, except instead of a minus sign in the superscript, I'm going to put a plus sign to signify that I'm looking at values of x to the right of a. And I'm looking at what happens to the function values as x approaches a from the right, or on the right-hand side. And so another way to think about these limits, and if we really wanted to evaluate the left-hand limit and the right-hand limit, what we could do is we could take the limit as some small number epsilon, some small positive number, epsilon goes to 0 of f of a plus epsilon. And similarly, that should be a minus epsilon. And similarly, we can take the limit as epsilon goes to 0 of f of a plus epsilon over here. And now here it's significant to note that epsilon is going to be a small positive number. So basically, I'm taking a for the left-hand limit and subtracting a small number and then letting that small number get really, really close to 0. Okay, so that's going to be the left-hand limit because I'm subtracting a little bit from a. So I'm going over here to a minus epsilon, and then I'm moving in towards a. And then the right-hand limit, I'm adding a little bit to a, and then moving in as epsilon goes to 0, a is going to approach a, or x is going to approach a from the right. And so this is going to be useful when we actually evaluate one-side limits, because we're going to be able to reduce the limit to looking at just a small positive number and letting that small positive number go to 0. So there's a very important thing to note looking at these one-sided limits, and that's this. The limit as x approaches a of a function f of x exists when, so here notice the left-hand limit is going to equal a number, and the right-hand limit is going to equal another number. So that's how we know that the limit doesn't exist. But now the limit will exist when the left-hand limit equals the right-hand limit. So this is a little bit more precise way to state when a limit exists. Really, we mean that the limit from the left, or the left-hand limit, equals the limit from the right, or the right-hand limit. Okay, so now we have a nice way to state when the limit of a function exists. So again, I'm just going to rewrite this to really emphasize that the limit as x approaches a of f of x exists if the limit as x approaches a from the left of f of x equals the limit as x approaches a from the right of f of x. So this kind of begs the question. So the existence of the limit depends on the left-hand limit and the right-hand limit equaling each other. But do the left-hand limit and the right-hand limit always exist? So the question is, do left-hand and right-hand limits always exist? If they do always exist, then we've really solved the limit problem. We just need to check whether these two numbers are equal to each other. But the problem is that the answer to this question is no. There are some strange functions that actually don't have left-hand and right-hand limits. So an example, and I'll show you a graph of what this function looks like on the next page, but the example is sine of 1 over x. So this is our function f of x. So for this example, the left-hand limit and the right-hand limit are not equal at x equals 0. So in other words, they don't exist at x equals 0. So let me write that down. So the limit as x approaches 0 from the right does not exist. So we can't even start talking about the limit as x approaches 0, because the limit as x approaches 0 from the right of this function does not exist. And so it's an interesting question. How could a right-hand limit not exist? It seems like if I just trace the function from the right, it should be approaching some number. Now it may not be approaching the same number that it's approaching from the left, but how could this happen? Well, let's look at the picture of the graph of this function. Okay, so here's the graph of the function sine of 1 over x. And now look what happens when we try to approach x equals 0. Let's just try to approach x equals 0 from the right. So I'm tracing the graph of my function and everything looks okay, but then I go up and then I shoot down and I shoot back up, and what I do is I start oscillating back and forth over and over again as I approach 0. As I get closer and closer to 0, my function sine of 1 over x, the graph is just oscillating extremely rapidly. And so instead of leveling off to just one y value that would give me the right-hand limit, I'm actually just bouncing between -1 and 1. So again, just to reiterate here, the limit is x approaches 0 from the right of this function does not exist. Now I'm not claiming that this function is super important beyond being what's called a counterexample to right-handed and left-handed limits existing. But now for the most part, the functions we're going to look at will have right-hand limits and left-hand limits that do exist. But it is very important to see these counterexamples and to have them in the back of your head if you ever think to yourself, well, do these things always exist? They don't. But hopefully that allows you to appreciate the fact that in most cases they exist. So let's look at an example of how you read off left and right-handed limits from the graph of a function. So A, the limit is x approaches 1. This minus means from the left. So here's x equals 1. So the minus means I'm going to trace the function from the left. So I go along the function and I'm going to let x approach 1 from the left. And what am I getting closer and closer to? I'm getting close to 1. Y equals 1. Now, even though I never quite reach y equals 1 from the left, the limit from the left is equal to 1. Okay, so now how about as x approaches 1 from the right? So let me trace the function from the right, and notice that I'm getting closer and closer and closer to y equals 0. Okay? So notice that even though this limit is not going to exist, so E says the limit is x approaches 1 of f of x, well, for the limit as x approaches 1 of f of x to exist, the left-hand limit needs to equal the right-hand limit, which they do not, so this does not exist. And it does not exist, again, because the left-hand limit does not equal the right-hand limit. So now let's look at the limit as x approaches 3 from the left. So I start tracing the graph of the function from the left of x equals 3, and I approach x equals 3 from the left, and it looks like I'm approaching y equals 2. Then I go from the right. What's the limit as x approaches 3 from the right? I just trace, and I get closer and closer to 3 from the right, and I'm approaching 2. Now, because the limit as x approaches 3 from the left of f of x is 2, and the limit as x approaches 3 from the right of f of x is 2, the left-hand limit equals the right-hand limit, so the limit as x approaches 3 exists and is equal to 2. Okay, so let's look at this function. It's piecewise defined, so it has different definitions for different parts of its domain, which its domain is going to be all real numbers. And we want to determine the values of a, for which the limit as x approaches a of f of x exists. But notice that if x is strictly less than -1, the function is just 2 minus x. And we know by the limit laws the limit is going to exist for all values for x less than -1. Same thing if x is strictly between -1 and 1, or if x is strictly greater than 1. All of these functions are just polynomials, so the limit is going to exist everywhere in those domains. There's no ambiguity about looking from the left and from the right, except at the points x equals -1 and x equals 1. So the potential problems are a equals -1 and a equals 1, because that's where two different pieces of the piecewise function meet, and we need to make sure that they line up for the limits to exist. So what we're going to do is we're going to try to evaluate the limit as x approaches -1 of f of x, and the limit as x approaches 1 of f of x, and see if those exist. And we're going to see if they exist by actually evaluating the left and right hand limits. So let's first look at a equals -1. So if we start with the left hand limit, so that's the limit as x approaches -1 from the left. Recall that this is equal to if I let epsilon be a very, very small positive number. Then this is just the limit as that positive number goes to 0 of f of -1 from the left. I want to subtract epsilon. And the advantage of doing this is going to tell me which piece of the function I need to look at. Now, if I subtract a positive number from -1, I'm going to be less than -1. So I need to use this top part of the definition. So this should be the limit as epsilon goes to 0 of 2 minus, here's what I'm plugging in for x. So 2 minus -1 minus epsilon. 2 minus x, and I'm plugging in -1 minus epsilon for x. And then if I let epsilon go to 0, well, that's just 0, and I just have 2 minus -1, which is 3. So here's half the puzzle. The limit from the left is equal to 3. Now let's look at the limit as x approaches -1 from the right. And again, if epsilon is just a small positive number, then I just want to take the limit as that small positive number goes to 0 of -1 plus epsilon. And now if I add a small positive number to -1, that's going to put me in this definition of the function. I'm going to be a little bit larger than -1. So this is just a limit as epsilon goes to 0 of -1 plus epsilon. But here again, I can just plug in epsilon going to 0, and I get -1. And here's the problem, right? So the limit from the left is 3, and the limit from the right is -1. These are not equal. But what can we conclude then? We can then conclude that the limit as x approaches -1 of f of x does not exist. So next, let's look at a equals 1. Okay, so same problem. Now we're just looking at a equals 1. We've already found that as x approaches -1, this limit does not exist. So what about as x approaches 1? Well, let's look at the left and right hand limits. So the limit as x approaches 1 from the left of f of x, we want to let epsilon be a very small positive number. And then this is just the limit as that small positive number goes to 0 of f of 1 minus epsilon. I just take away a little bit to look to the left of x equals 1. And 1 minus epsilon is less than 1 by just a little bit. So we're in this middle definition of the function. So this is just the limit as epsilon, that small positive number, goes to 0, of 1 minus epsilon. But that's just 1. I can just plug in epsilon equals 0. How about from the right? The limit as x approaches 1 from the right, same deal. We just let epsilon be a small positive number. Take the limit as epsilon goes to 0, but this time we want to add epsilon to 1 to be to the right of 1. And then we're in this final definition of the function, x minus 1 squared. So what is this? It's the limit as epsilon goes to 0 of 1 plus epsilon minus 1 squared. And now look, if epsilon goes to 0, this is just 1 minus 1, which is 0 squared. So the limit is just 0. So here are my two limits, from the left and from the right. And again, notice that they're not equal. So this limit, the limit as x approaches 1, also does not exist. So what's my answer to this question? Determine the values of a for which the limit exists. Well, it's all real numbers. We already talked about that, except x equals negative 1 and x equals 1. So here you have to evaluate some more one-sided limits. So the key is we're approaching 1 from the left, so we want to take epsilon to be a very small positive number. And we want to take the limit is that small positive number goes to 0 of, well, instead of just taking x here, I actually want to plug in 1 minus epsilon. That's what this minus is telling me, really. I want to take away a little bit from 1. So this should be, everywhere I see an x, I'm going to put a 1 minus epsilon. Okay, so now, what's our favorite thing to do? Do some algebra. So let's simplify what's going on here. So this is 1 minus epsilon plus 3. So that seems to be 4 minus epsilon. And then, what else do we have? We have 1 minus epsilon minus 1. Well, that's just going to be absolute value of minus epsilon divided by, again, 1 minus 1 gives me 0, and I'm just left with minus epsilon. But here you're really going to see the advantage of using epsilon being a positive number, because the absolute value of this number is just going to be epsilon, because negative epsilon is a negative number. So when I take the absolute value, I'm just going to get positive epsilon. So this is really limit as epsilon goes to 0 of 4 minus epsilon times epsilon over minus epsilon. But epsilon over minus epsilon is just negative 1. So this is just the limit as epsilon goes to 0 of 4 minus epsilon times negative 1. And recall that I can actually cancel these factors of epsilon because I actually don't want to consider the case when epsilon is equal to 0, only when epsilon is really, really close to 0. Okay, but now if I let epsilon go to 0, this goes to 0, and I just have 4 times -1, so the limit is equal to -4. Okay, another one-sided limit. And this is actually an interesting example because we're not just arbitrarily choosing to take the limit from the right here. It actually doesn't even make sense to talk about taking the limit as x approaches 2 from the left here, because if I just look at the domain of this function, let's say that this function is f of x. Well, the domain of f, what are the numbers I can plug in for x? Well, first of all, I can't plug in 2 because that's going to make the denominator 0. And I also can't plug in any number less than 2 because that's going to make a negative under the square root. So the domain here really is just 2 to infinity. So you see that it wouldn't make sense to look to the left of 2. It doesn't even make sense to look at x equals 2. It only makes sense to look as x approaches 2 from the right. So this limit, if I take epsilon, again, to be a very small positive number, then I just want to take the limit as epsilon goes to 0 of, well, when I see an x, I'm just going to replace it with 2 plus epsilon. So this is going to be 2 plus epsilon minus 2 over square root of 2 plus epsilon minus 2. But this simplifies a little bit. The 2's actually cancel. And what am I left with? I'm left with epsilon on top and square root of epsilon on bottom. And now recall that epsilon is a positive number. So here I'm taking the square root of a positive number. So there's no problem here. And epsilon is not going to be 0, so I can actually cancel a factor of square root of epsilon. And let me just do some scratch work. This is like epsilon over epsilon to the 1/2. So square root is like to the power of 1/2. So this is like, if I use my properties of exponents, epsilon to the 1 minus 1/2, which is epsilon to the 1/2. Just an algebraic reminder. So this is really just the limit as epsilon goes to 0 of square root of epsilon. But that's just 0. Easy enough. So this one-sided limit, right-hand limit, is equal to 0.